Hello, this is Ishita, and this is the fourth episode of Explore Space with me. Many of us know that these scary, mysterious objects exist in our universe called black holes, but how many of us actually know what's a black hole? A black hole is an astronomical body so compact that its gravity prevents anything, including light, from escaping. Albert Einstein's theory of general relativity, which describes gravitation as the curvature of spacetime, predicts that any sufficiently compact mass will form a black hole. Black holes typically form when very massive stars collapse at the end of their life cycle. After a black hole has formed, it can grow by absorbing mass from its surroundings. Supermassive black holes of millions of solar masses may form by absorbing stars and merging with other black holes, or via direct collapse of gas clouds. There is consensus that supermassive black holes exist in the centers of most galaxies. Quantum field theory in curved spacetime predicts that event horizons emit Hawking radiation, with its rate of emission being inversely proportional to its mass. This causes the black hole to lose mass very slowly, provided it is not accreting matter. However, even the smallest class of black holes observed, stellar black holes, are gaining mass from the cosmic microwave background radiation faster than they are losing mass via Hawking radiation. The presence of a black hole can be inferred through its interaction with matter and electromagnetic radiation, such as visible light. Matter falling towards a black hole can form an accretion disk of infalling plasma, heated by friction and emitting light. In extreme cases, this creates a quasar, some of the brightest objects in the universe. Merging black holes can be detected by the gravitational waves they emit. If stars are orbiting a black hole, their motions can be used to determine the black hole's mass and location. In this way, astronomers have identified numerous stellar black hole candidates in binary systems and established that the radio source, known as Sagittarius A, at the core of Milky Way galaxy, contains a supermassive black hole of about 4.3 million solar masses. Now, we will learn about the anatomy of a black hole. Event horizon. This is what makes a black hole black. We can think of the event horizon as the black hole surface. Inside this boundary, the velocity needed to escape the black hole exceeds the speed of the light, which is as fast as anything can go. So whatever passes into the event horizon is doomed to stay inside it, even light. Because light can escape, black holes themselves neither emit nor reflect it, and nothing about what happens within them can reach an outside observer. But astronomers can observe black holes thanks to the light emitted by surrounding matter that hasn't yet dipped into the event horizon. Now we will talk about the accretion disk. The main light source from a black hole is a structure called an accretion disk. Black holes grow by consuming matter, a process scientists call accretion, and by merging with other black holes. A stellar mass black hole paired with a star may pull gas from it, and a supermassive black hole does the same from the stars that stay too close. The gas settles into a hot, bright, rapidly spinning disk. Matter gradually works its way from the outer part of the disk to its inner edge, where it falls into the event horizon. Isolated black holes that have consumed the matter surrounding them do not possess an accretion disk and can be very difficult to find and study. If we could see it up close, we would find that the accretion disk has a funny shape when viewed from most angles. This is because of the black hole's gravitational field warps space-time, the fabric of the universe, and light must follow this distorted path. Astronomers call this process gravitational lensing. Light coming to us from the top of the disk behind the black hole appears to form into a hump above it. Light from beneath the far side of the disk takes a different path, creating another hump below. The hump's size and shape changes as we view them from different angles, and we see no humps at all when seeing the disk exactly face on. Then comes the event horizon shadow. The event horizon shadow captures any light passing through it, and the distorted spacetime around it causes light to be redirected through gravitational lensing. These two effects produce a dark zone that astronomers refer to as the event horizon shadow, which is roughly twice as big as the black hole's actual surface. Now we will talk about the photon sphere. From every viewing angle, the thin rings of light appear at the edge of the black hole shadow. These rings are really multiple, highly distorted images of the accretion disk. Here, light comes from the disk, actually orbits the black hole multiple times before escaping to us. Rings closer to the black hole become thinner and fainter. Now we will talk about Doppler beaming. Viewed from most angles, one side of the accretion disk appears brighter than the other. Near the black hole, the disk spins so fast that an effect of Einstein's theory of relativity becomes apparent. Light streaming from the part of the disk spinning towards us becomes brighter and bluer, while light from the other side of the disk rotating away from us becomes dimmer and redder. This is the optical equivalent of an everyday acoustic phenomenon where the pitch and the volume of a sound, such as a siren, rise and fall as the source approaches and passes by. The black hole's particle jets show off this effect even more dramatically. This is called the galaxy's corona. It's been called one of the most extreme physical environments in the universe. Strong magnetic fields threading the inner accretion disk extend out of it, creating a tenuous, turbulent billion-degree cloud. Particles in the corona orbit the black hole at velocities approaching the speed of light. It's a source of X-rays with much higher energies than those emanating from the accretion disk. But astronomers are still trying to figure out its extent, shape, and other characteristics. In black holes of all sizes, something strange can occur near the inner edge of the accretion disk. A small amount of material headed towards the black hole may suddenly become rerouted into a pair of jets that blast away from it in opposite directions. These jets fire out particles at close to the speed of light, but astronomers don't fully understand how they work. The jets from supermassive black holes, the type found in the center of most galaxies, can reach lengths of hundreds of thousands of light years. In cases where these jets happen to angle into our line of sight, we may only easily detect that one firing towards us due to Doppler beaming. This process makes the near jet considerably brighter but greatly dims the rear jet. This is a singularity that you see on the screen. General relativity predicts that the very center of a black hole contains a point where matter is crushed to infinite density. It's the final destination for anything falling into the event horizon. The singularity may be either a physical structure or a purely mathematical one, but right now astronomers don't know which is true. The prediction of a singularity may signal the limits of relativity, where quantum effects not included in the theory become important in a more complete description of gravity. There are mainly two types of black holes, stellar black holes and supermassive black holes. When a massive star is around 20 times the sun's mass or more, the star's core collapses into a stellar mass black hole. The picture that you're seeing right there on the screen is a simulated picture of a black hole, stellar black hole. The masses of these newly born objects can range from a few hundreds of times the sun's mass, depending on star's mass when the supernova began. Stellar mass black holes can continue to gain mass through collisions with stars and other black holes. Nearly all the stellar mass black holes observed so far have been found because they are paired with stars. They likely originated as mismatched stars where the more massive one evolved rapidly into a black hole. In some cases called X-ray binaries, the black hole pulls gas of the star into a disk that heats up enough to produce X-rays. Binaries have revealed around 50 suspected or confirmed stellar mass black holes in the Milky Way, but scientists think there may be as many as 100 million in our galaxy alone. Supermassive black holes. Almost every large galaxy, including our Milky Way, has a supermassive black hole at its center. These monster objects have hundreds of thousands to billions of times the Sun's mass, although some scientists place the lower boundary at tens of thousands. The one at the center of our galaxy, Sagittarius A, is 4 million times the mass of the Sun, relatively small compared to those found in some other galaxy. For example, black hole at the center of galaxy Holmberg 15A holds at least 40 billion solar masses. The biggest black hole to be ever discovered is Phoenix A and has an estimated mass of 100 billion solar masses. Scientists aren't sure how these monster objects came to be. Observations of distant galaxies show that some supermassive black holes formed in the first billion years after the birth of the universe. It's possible these black holes began with the collapse of supermassive stars in the early universe, which gave them a head start. While their origins are mysterious, scientists know supermassive black holes can grow by feeding on smaller objects like their stellar mass relatives and neutron stars. They can also merge with other supermassive black holes when galaxies collide. There are mainly two types of active galactic nuclei. One is a quasar and one is a blazar. A quasar is an extremely luminous, active galactic nucleus. It is sometimes known as a quasi-stellar object, abbreviated as QSO. The emission from an AGN is powered by accretion onto a supermassive black hole with a mass ranging from millions to tens of billions of solar masses. Surrounded by a gaseous accretion disk, gas in the disk falling towards the black holes heats up and releases energy in the form of electromagnetic radiation. The radiant energy of quasars is enormous. The most powerful quasars have luminosities thousands of times greater than that of a galaxy such as the Milky Way. A blazar is an active galactic nucleus with a relativistic jet, a jet composed of ionized matter traveling at nearly the speed of light, directed very nearly towards an observer. Relativistic beaming of electromagnetic radiation from the jet makes blazars appear much brighter than they would be if the jet was pointed in a direction away from Earth. Blazars are powerful sources of emissions across the electromagnetic spectrum and are observed to be sources of high-energy gamma-ray photons. Blazars are highly variable sources, often undergoing rapid and dramatic fluctuations in brightness on short timescales, hours to days. Some blazar jets appear to exhibit superluminal motion, another consequence of material in the jet traveling towards the observer at nearly the speed of light. Thank you for watching this video to the end. We come to the end of our lesson. Please like, share, and subscribe to my channel. And please also check out my website.